Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today, we are continuing with differentiation, looking at the parametric representation of curves. So if you're ready to learn, then let's get into it. So parametric representation refers to when our function, so y and x, are in terms of, or a function of, another parameter. So here, with what I've written, this other parameter is t. And throughout physics, a lot of the time, this other parameter will be time, so t for time, but it doesn't have to be, time can equal or doesn't have to equal time here. T doesn't have to equal time. So if I give an example of this, let's say for our first example, x equals a cos of t and y equals b sine of t. And as you can see, this matches our parametric representation. We can eliminate t here by using our trigonometric identities, and we know sine squared plus cos squared always equals 1. So if we rearrange these, we would have our sine squared is y squared over b squared, plus our cos squared, which is x squared over a squared, equals 1. And this is the function for an ellipse, and I'll draw that for you now. So as you can see, this is what an ellipse looks like. You may be familiar with it, and if we just look at when are we going to be crossing each axis, we're going to have crossing the x-axis at a and minus a, and how do we get a or minus a? It will be when cos t is 1 or minus 1, which would result in sine t being 0. And that is going to be at 0 and pi, and then when y is b or minus b and sine is 1 or minus 1. So we have our t equaling 0, pi over 2, pi and 3 pi over 2 to get round to each point that crosses the axes. And obviously adding 2 pi to each of these t values will result in the same point, so that's due to cos and sine being a wave that's repeating. And so from here we can just a quick sanity check. If we had a equaling b, this would turn into a circle for a equals b. Just from the graph you can see if they were equal, that will squish it in or expand out vertically into a circle. And if we look at our equation over here, we're going to have y squared over a squared plus x squared over a squared equaling 1, or x squared plus y squared equals a squared, which is the equation for a circle. So quick sanity check, you can see that this ellipse will turn to a circle for a equaling b, but obviously an ellipse is a more general term to refer to any of these sort of graphs. And a value to do with ellipses, which will come in handy throughout physics, but especially in astrophysics when you're looking at orbiting bodies, that they orbit in an elliptical path. And a parameter to do with that is the eccentricity of your ellipse, e, and that can be found by the equation b equals a 1 minus e squared to the power of a half. And just as a sanity check, a circle should have an eccentricity of 0. It's not eccentric in any direction. And so if we just look at when it is a circle, a equals b, so this equation will become 1 equals 1 minus e squared to the half, i.e. e squared equals 0, therefore e equals 0 for a circle. So this equation will come in handy later on and you'll see how it's derived, but for now we've just solved this parametric representation and we've been able to draw it knowing that ellipses look like this. So for our next parametric function that we'll draw, we'll look at x equaling a times t minus sine t, and y equaling a times 1 minus cos t. And if we were just to start drawing this, we might want to look at what's the maximum and minimum of y, and then see how x evolves. And as we can see that these are going to be sort of sinusoidal in some way, we'll know they'll repeat. And the special case last time was we could eliminate t and find an explicit function of y equaling a function of x. But here we can't do that. So let's start with just looking at what's the maximum y could be. Well, it could be a times 1, and what's the maximum that minus cos could be? It could be plus 1 if cos was minus 1, so minus 1. And so that's going to give us a maximum of 2a, and the minimum is if cos was plus 1, and that will lead to 0. So y goes between 2a and 0, maximum to minimum. And this is obviously assuming that a is positive. So we could just start by drawing our axes, and we know that it's not going to be going below 0. So we could put our 0 here and 0 here, and as it's repeating, it doesn't matter that it's starting at 0 here, you can imagine it will repeat on the other side of the y-axis. So where is it starting at 0, 0? Well, is x going to be 0 when t is 0 and y is 0? Yes, so this side, when t is 0, this x is going to equal 0, and when t is 0 over here on y, it's going to be 1 minus 1, so we'll also have 0 here. So it will start at 0, 0, and it will go up to a value of 2a, and it will reach our maximum height of 2a when t is equal to pi, because then cos t will equal minus 1. And what we can do is, it will reach this point over here, t is pi, and as this is the maximum, it will be going back down again to 0, and that will happen at 2 pi a. And as you can see, this whole time, all that's happening is x is increasing along, and the contribution is going between 1 and minus 1 for our sine t. But when it's crossing the x-axis, or when it's just touching it, it's going to be just dependent upon this t value here, because our sine t will always equal 0 when it's our y equals 0, because cos and t are sort of anti-symmetric in that sort of way. They overlap in the wrong point, if you know what I'm trying to say. So that's 2 pi a, and that's because its t is 2 pi, and so this will just continue in this sort of fashion, and that will be 4 pi a, and you get the picture. And this is because here t is 2 pi, here is 4 pi, and it would also be the same in the minus 2 pi, minus 4 pi, etc. And obviously here as well is t equals 0. Today we've learnt about the parametric representation of curves. In the next video we'll be looking at polar coordinates, so if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.